There are factories in America where no camera has ever been allowed to film. And inside those walls, steel becomes guns under tight secrecy. According to the most recent ATF data, U.S. manufacturers produced about 9.8 million firearms in 2023. Yet only a handful of technicians nationwide hold clearance to witness the full process from melting metal to finishing the trigger. For most people, these plants remain rumors, silent, fenced, and heavily guarded. Today, Captain Discovery steps past those gates.
Caliber machine gun barrels. That's what they're making right now.
You will see how a modern gun is born, inside a place the world was never meant to witness. The story of the gun began more than 1,000 years ago, when black powder changed how humans fought and hunted. Early weapons were simple tubes of metal, loud and unpredictable. Centuries later, the Industrial Revolution reshaped them into precision machines. In America, factories turned that craft into an assembly line science, feeding battlefields, law enforcement, and sport shooters alike. By the mid-1900s, the nation's production power had made the firearm both symbol and tool, part of its culture and its industry. Today, that legacy lives on in guarded plants where craftsmanship meets automation, and every spark of metal carries a century of history. Every gun begins with metal. Large steel billets arrive at the factory by truck, each one tested for purity and tensile strength. Workers log the batch numbers and send samples for chemical analysis before machining begins. Inside the plant, robotic cranes feed these billets into massive CNC machines designed to cut, bore, and mill every contour with sub-millimeter accuracy. Coolant sprays constantly to prevent heat distortion, while sensors track temperature and pressure. One line can produce hundreds of precision parts a day, from frames and barrels to slides and bolts. Every cut is measured twice. Even a fraction too deep could ruin a piece worth thousands of dollars.
What you're about to see is this machine taking what we've just seen come out of the honing machine and put it into a cold hammer forging machine.
When the cycle ends, a human inspector checks each surface under bright white light before the metal moves to the next stage. Here, raw strength meets geometry, the moment steel starts its transformation into a working firearm. Once the main pieces are machined, the work shifts to precision shaping. Hydraulic presses bend and stamp each frame to exact tolerances, forcing the metal into alignment within thousandths of an inch. In one section, the barrel is honed using rotating diamond tools that carve microscopic grooves, known as rifling, responsible for a bullet's spin and accuracy. Robotic arms hold every part steady, as pressure gauges and digital calipers verify dimensions in real time. Any defect, even invisible to the eye, could cause the weapon to jam or misfire under pressure. Nearby, technicians assemble trial sets, frames, slides, and barrels, testing how smoothly they fit together. The sound of metal sliding against metal echoes through the plant, precise and mechanical. Only after a part passes this alignment test does it move to surface finishing and heat treatment. Before a gun can fire safely, its metal must survive extreme stress. Each machined part, especially the barrel and firing chamber, is placed into a heat treatment line. Conveyor trays carry the pieces into a furnace glowing at over 1,500 degrees Fahrenheit, where steel molecules realign for strength. At that temperature, the metal softens, then hardens again as it cools in a controlled oil bath. Once hardened, each part must be finished to perfection. Steel surfaces move through a polishing line where rotating belts smooth away tool marks. Barrels and frames are coated to resist corrosion, either blued, anodized, or treated with ceramic layers for modern models. In the assembly hall, workers and robots share the same rhythm. When the mechanical structure is complete, optics, safeties, and triggers are installed. Inside the testing range, thick concrete walls absorb the echo of controlled explosions. Each firearm is mounted on a mechanical rig that fires several live rounds while sensors record recoil, pressure, and barrel temperature. Technicians behind bulletproof glass monitor every flash, ensuring the weapon cycles and ejects properly. If a round jams or misfires, the gun is pulled from the line and rebuilt from scratch. In this room, there's no margin for error. Even the smallest flaw can turn precision into danger. If you believe safety should always come before speed, hit like to support those who build with care. Once a gun passes, it's cleaned, stamped with certification, and entered into the manufacturer's registry for traceability. From there, it's packaged and shipped to distributors and law enforcement under federal oversight. Perfection ends here only for the machine. For the bullet, the process is just beginning. A single bullet holds more power than its size suggests. In less than a millisecond, it creates an explosion hotter than fire and faster than sound. Factories that make them work under the strictest safety codes in American industry, where even static electricity can trigger disaster. Here, brass coils the size of truck tires are punched, stretched, and filled with chemical energy measured to a fraction of a grain. Every spark, every vibration is controlled. Because one mistake doesn't ruin a product, it destroys the room. So how do they shape something this dangerous into the most reliable component of modern weapons? The first bullets were simple lead balls, hand-loaded with loose powder and paper wadding. They worked, but they were slow, messy, and unpredictable. By the 1800s, engineers developed the metal cartridge, combining primer, powder, and bullet into a single unit. It made firing faster, cleaner, and far more reliable. Factories soon replaced hand-loading with automated presses, producing thousands of identical rounds each day. During both World Wars, American plants became the center of that production, refining the standards still used today. Before a bullet ever meets gunpowder, it starts in a noise-filled press room. Brass rolls the width of a car are fed into automated stamping lines that never stop. Each punch cuts hundreds of circles per minute, each one the embryo of a cartridge case. Mechanical arms collect them and feed them forward, where hydraulic dies pull the flat discs into shape. The metal stretches, thins, and cools in seconds, transforming from sheet to shell under precise control. Freshly formed shells are still too brittle to handle the explosion waiting inside them. To make them strong yet flexible, they must be softened with heat. The cases travel through a long tunnel furnace glowing orange, heated to over 1,200 degrees Fahrenheit. At that temperature, the brass relaxes, releasing stress from the earlier forming process. After heating comes washing. Residue from forming and oxidation is scrubbed away in massive rotating drums filled with water and mild acid. After annealing, the brass moves to precision stations where the case mouth is formed. Mechanical dies gradually narrow each opening to match its specific caliber. This is where accuracy begins. The neck must grip the bullet tightly enough to hold pressure, but not so tight that it distorts the shape. Automatic feeders push thousands of cases into position every minute. Rotating blades trim each one to an exact length, shaving away microscopic edges left from earlier forming. After trimming, cases move to the station that forms the primer pocket. A closed die process shapes the base, so a primer will sit flush and centered every time. High-speed punches form the pocket, while lasers verify depth and concentricity in real time. Next comes final cleaning. Cases tumble through ultrasonic baths that dislodge oil, scale, and microscopic debris from forming. They rinse under filtered water and dry in heated tunnels to prevent corrosion. A visual inspection line follows, where cameras and humans scan for surface blemishes or small deformities. Priming is the next delicate step. Automated systems insert a primer into each pocket, seating it to a controlled depth. From there, measured charges of propellant are dispensed with high-precision metering systems calibrated constantly. After the charge, bullets are placed and seated to exact depths. A crimping station secures the bullet, locking case and projectile together for uniform pressure and safe feeding. Sample rounds are test-fired under controlled conditions to verify pressure and velocity parameters. Batches that fail either go to rework or are destroyed under strict disposal protocols. Finally, approved ammunition is boxed, labeled by lot, and logged to enable complete traceability. There's another side to this story. Items meant to stop bullets, not make them. There are factories where sheets of fiber and polymer become life-saving armor. Unlike guns and ammunition, these workshops build protection, not propulsion. When a bullet hits, you have less than a millisecond to live or survive. In that instant, everything depends on a few millimeters of fabric. According to NIJ standards, ballistic vests must absorb over 300 foot-pounds of energy without penetration. Behind that number lies years of material science and human testing. How do these layers stop a bullet and still let a person move? We'll find out. Today, Captain Discovery takes you inside a facility where threads are turned into shields. Centuries before modern fabric, soldiers relied on metal plates and chainmail to block blades and arrows. But bullets changed everything. In the early 1970s, chemists at DuPont created a synthetic fiber called Kevlar, 5 times stronger than steel by weight. It was light, flexible, and could catch projectiles instead of breaking apart. Police departments adopted it first, followed by military units worldwide. Over time, new fibers like Dyneema and Spectra pushed protection even further, making today's bulletproof vests thinner, lighter, and tougher than ever. The process begins with raw rolls of high-performance fibers such as Kevlar or Dyneema. Each roll stretches hundreds of meters and must remain free of dust or moisture. Large automated tables pull the fabric layer by layer. Computer-guided cutters trace digital patterns designed for different vest sizes. The blades move fast but precise, up to 4,000 cuts per hour with less than 1 millimeter deviation. Every panel cut must match the ballistic design approved by the National Institute of Justice. They may look like ordinary fabric now, but what happens next will turn these soft layers into something that can stop a bullet. In the lamination room, precision heat and pressure transform the fabric stacks into ballistic panels. Each layer is arranged in a clean air environment to prevent dust from weakening the bond. Once loaded into a hydraulic press, the panels are exposed to heat above 250 degrees Fahrenheit and pressure reaching 20 tons per square foot. Inside the chamber, resin sheets melt and flow between fibers, locking them together into a single, flexible composite. But before they're assembled, each piece must face something far harsher than machinery: real bullets traveling faster than sound. Technicians mount each panel in a frame that mimics a human torso or curved target. High-speed cameras capture the moment of impact at thousands of frames per second. Sensors record velocity, energy transfer, and backface deformation in precise numerical detail. Test rounds range by caliber and velocity to match NIJ performance levels for each armor class. After each shot, engineers measure how much the rear surface flexed without penetration. Rejected panels go to forensic analysis to find material faults or bonding issues. Successful panels are logged with batch numbers and kept for certification records. If you would trust your life to this panel, type yes below. If you'd want to see more testing data first, type "Show me the numbers." Once panels pass ballistic tests, they move to final shaping and assembly. CNC cutters trim each panel to the exact pattern for a given vest size and model. Edges are sealed and reinforced to prevent fraying during stitching and use. Stitching machines sew heavy-duty seams while operators add modular webbing and attachment points. Velcro, quick-release buckles, and plate pockets are installed according to spec for rapid donning and field use. Every seam is tension tested to confirm durability under repeated stress. Fit testing follows assembly. Before any vest can be sold or issued, it faces one final round of scrutiny. Inspectors open random boxes from each batch and review every document against production records. Next comes stress testing. Finished vests are flexed thousands of times in automated rigs that simulate months of field movement. Humidity chambers expose them to heat, sweat, and moisture to ensure materials don't separate or weaken. Hardware, buckles, zippers, Velcro, is pulled and released repeatedly to check for fatigue. From molten steel to polished barrels, from raw brass to live ammunition, and from soft fibers to armor strong enough to stop a bullet, Each of these factories tells a different story about power, precision, and protection. Every machine, every spark, every layer of fabric exists for one purpose: control. Control of force, of safety, of the fine line between creation and destruction. Most of us will never see these processes firsthand, yet they shape the world we live in every day. From the police officer's vest to the hunter's rifle locked away at home. What surprised you the most about how these products are made? Leave your thoughts in the comments. We read everyone. And if you want to keep exploring the hidden side of manufacturing, don't forget to subscribe to Captain Discovery. New episodes are already in production, taking you deeper inside the machines that build modern life.